Hello everyone, my name is Maurya Gottipati and I am thrilled to be here today to share our machine learning project with you. The project is titled Comparative Analysis of Fire Image Recognition using MobileNet and ShuffleNet models. In this study, we explore and compare the performance of two powerful architectures, MobileNet and ShuffleNet, specifically in the task of fire image recognition. I am proud to be presenting this work alongside my talented teammates Santosh Rahul and Sneha Pallaboina. Together, we have dwelled into how these models handle the critical task of recognizing fire in images, which has significant implications for safety and emergency response technologies. Let's dive into how these models perform and what we have discovered through our research. Thank you for joining us, and I hope you find our findings as exciting as we do. Let's get started. First, let me introduce some key aspects of our project. Those are dataset overview, choice of architectures, project objectives. For our analysis, we utilized the widely recognized fire dataset from Kaggle. This dataset is a staple in classification tasks due to its diverse and complex fire images, making it an excellent testbed for assessing the robustness of our chosen models. Our focus was on two state-of-the-art architectures, MobileNet and ShuffleNet. These models are celebrated for the high efficiency in environments with limited computational resources, which makes them ideal for applications requiring fast, effective real-time image processing. The primary goal of our project is to perform through comparative assessment of these architectures. We have explored a range of hyperparameters, including different number of iterations and batch sizes. Our aim was to meticulously understand how these variables affect each model's ability to accurately recognize fire in images. Welcome to our exploratory data analysis session, where we dwell into the specifics of our dataset. Here are few representative images. Those featuring fire are labeled as 1 and those without fire are labeled as 0. Below you will find histogram plots depicting the size distribution of fire and non-fire images. Most images range between 0 and 2000 in both height and width dimension. As we move to the next slide, you will observe that our dataset comprises 755 fire images and 244 non-fire images, totaling 999 images. Displayed next is a bar plot that illustrates the distribution between fire and non-fire images. In conclusion, the dataset permanently features a significant majority of fire images compared to non-fire images. Notably, it is important to mention that among the non-fire images, image 189 has experienced loading issues. Let us move to next slide. MobileNet, lightweight model for mobile devices. In this slide, we discuss the core principle underlying the MobileNet architecture, which is a depth-wise separable convolutions. The innovative approach redefines how we think about building and optimizing models, particularly for mobile and embedded systems. Let's break down the structure of depth-wise separable convolutions. Firstly, depth-wise convolution. Unlike traditional convolutions that apply filters to entire input volumes, depth-wise convolution operates on each channel independently. This means that if an image has three channels like red, green and blue, a separate filter is applied to each color channel, preserving the distinct characteristics captured in each. Following the depth-wise layer, we have the point-wise convolution, also known as 1 cross 1 convolution. This layer's role is pivotal as it combines the outputs from depth-wise convolution. Here, the 1 cross 1 convolution acts to mix the information, allowing the model to learn from across the separate channels and effectively adjust the dimension for further processing. Now let's talk about the advantages. Efficiency. Depth-wise separable convolutions dramatically reduce the computational cost by approximately 8 to 9 times compared to standard convolution. Secondly, it is compact. The model is simpler and has a smaller size, making it less burdensome for memory and faster in performance, which is crucial for real-time applications. Speaking of applications, these convolutions are ideal for real-time object detection, video classification, and face recognition, all tasks that require high efficiency and speed, especially in mobile or embedded systems where resources are constrained. Let us move to next slide. MobileNet architecture. In this segment of our presentation, we will delve into the MobileNet architecture that we have utilized in our project. Here, we represent the layers, output shapes, and parameters. The input to our model is an image with a shape of 320 by 320 pixels and 3 color channels. Our model outputs a shape of 2, corresponding to our classification categories. Those are fire and non-fire images. Here are the key statistics of the MobileNet model we have implemented. 8,03,202 are total parameters, in which 7,98,722 are trainable parameters and 4,480 are non-trainable parameters. Let's move to next slide. ShuffleNet, efficient CNN architecture with channel shuffle. Welcome to our exploration of the ShuffleNet architecture, a model renowned for its exceptional efficiency and adaptability. Today, I am excited to highlight its core feature, the channel shuffle. What is channel shuffle? It is a revolutionary mechanism that enhances information flow across different groups within the network. By rearranging the output channels of group convolutions, ShuffleNet ensures that subsequent layers receive a mix of inputs from all previous groups. This is not only enhances future representation but also fosters robustness in learning. Advantages of ShuffleNet. Efficiency. ShuffleNet dramatically reduces computational costs, which makes it ideal for scenarios where processing power is a premium. Despite fewer parameters, it maintains commandable accuracy. Scalability. The architecture offers flexibility in adjusting the number of groups, allowing it to cater to various computational budgets and accuracy requirements. Speaking of applications, ShuffleNet is suitable for mobile devices and environments requiring high efficiency with limited computational resources. In summary, ShuffleNet's integration of channel shuffle makes it standout choice for efficient and effective deep learning across diverse applications. Let's move to next slide. In this part of our presentation, we focus on the ShuffleNet architecture, a pivotal element for our project, renowned for its efficient channel shuffling capability. This feature plays a critical role in our model's ability to handle complex datasets efficiently. Here are the key statistics of the ShuffleNet model we have implemented. 6,78,770 are total parameters, in which 6,71,762 are trainable parameters and 7,008 are non-trainable parameters. Let us move to next slide. These are the results obtained from our project with normalization applied to the model, trained with various iterations and a batch size of 32. The metrics are displayed for different configurations with the optimal metrics highlighted in red. Let's explore more results. In these results, the batch size is reduced to 16. Let's go to next slide. These are the results obtained from our project without normalization, trained with various iterations and with batch size of 32. The metrics are displayed for different configurations with the optimal metrics highlighted in red. In these results, the batch size is reduced to 16. Overall, the metrics highlighted in red indicate optimal performance compared to any other configurations of hyperparameters. Let us move to next slide. Discussion on model performance across different training configurations. The configurations varied by hyperparameters like number of epochs, batch size, along with normalization as we seen earlier. Epoch and batch size influence. As the number of epochs increases, the MobileNet and ShuffleNet generally shows improvements in accuracy, precision and F1 scores. This trend suggests that more training allows the model to better generalize. Reducing batch size from 32 to 16 consistently led to better performance in terms of precision and F1 score, possibly due to more fine-grained update in model weights. MobileNet was a ShuffleNet. MobileNet often outperforms ShuffleNet in accuracy and precision across similar settings, highlighting a higher efficiency in learning. ShuffleNet trains faster than MobileNet, which illustrates a speed versus performance trade-off. Normalization impact. Normalization doesn't markedly enhance performance. It sometimes reduces key metrics like accuracy and precision, indicating limited benefits for these specific models and data. Optimal performance. The highest recorded performance of MobileNet came at Epoch 15 with a batch size of 16, achieving an accuracy of 0.98, precision of 0.974, and an F1 score of 0.987. ShuffleNet peaked in the same configuration with slightly lower metrics but still impressive, demonstrating the effectiveness of longer, more granular training. Let's move to next slide. Conclusion. Training duration versus performance. There is clear correlation between longer training times, improved model performance. However, it is crucial to balance the increased computational cost with the gains in metric improvements. Model selection. MobileNet, despite being slower, would be preferable for scenarios where accuracy and precision are crucial. ShuffleNet offers a viable alternative when speed and computational efficiency are critical. Optimal training configuration. For tasks similar to the ones tested, a smaller batch size and a higher epoch count seem beneficial for maximizing performance. Normalization role. Normalization impact can vary and its use should be tailored based on empirical results per dataset and tasks. Thank you.